Hello students, this is a review of the material that you're going to be looking at for test number 2. This is in MAT120, the Elementary Statistics College Now class that I teach. If you need any more help with this elementary statistics material, there are many videos that are on the website for the class that you can take a look at, some from Khan Academy, some from other places. I'm going to go over some of the answers to these questions and I'll try to walk you through the concepts involved. The first answer that I want to take a look at is suppose that probability of A is 0.4 and B is 0.2. The important part here is that events A and B are so-called mutually exclusive events. If events are mutually exclusive, that simply means ME means that they cannot happen at the same time. For example, when you flip a coin, it's mutually exclusive to have heads and tails because those two things don't happen at the same time. That helps us figure out the probability of A and B. Well, they can't happen at the same time. They are mutually exclusive. They can't coincide. The probability of A or B, that formula is the probability of A plus the probability of B minus the probability of A and B. Well, we know A and B is 0, and we know these two probabilities, so it's a very simple process. A given B is a formula that you must remember. It's the probability of A and B over the probability of B. This was easy to calculate because 0 divided by anything, with the exception of 0, is equal to 0. All right. Number 2 is different. Number 2 talks about events being independent. Remember that independent means that their probabilities don't affect each other. I guess it was silly for me to write this because I already wrote it here, but that's fine. The probability of A and B, when two events are independent, finding the probability of A and B is as simple as multiplying the probability of A times the probability of B. That's how we got 0.21. The probability of A or B, remember, it's that same formula from before, but in this case we have a probability of A and B. So 0.3 plus 0.7, that's A and B. And then the probability of A and B, that's going to be 0.21. We calculate that to be 0.79. Last but not least, we use the same formula from above here. The probability of A and B is 0.21. The probability of B is 0.7. So 3/10 is our answer. You put this in the calculator and find the fraction. For question number 3, it gives us the probability of B and the probability of A and B. This helps us find the probability of A given B. That's the same formula as above here. We were able to figure this out pretty effectively. We can't find the probability of B given A, however, because this is the probability of B given A, and we don't know the probability of just A. So, unfortunately, we can't figure it out. For events A and B being mutually exclusive, we know that the probability of A and B is not equal to 0, which means that they can happen at the same time, which also means that they are not mutually exclusive. If probability of A is equal to 0.45, this is different than the information they gave us up here, are events A and B independent? Well, independent means A is going to happen at the same probability regardless of what B happens, or what B is going to do. A given B should be the same as A if they're independent, because given B doesn't matter. It doesn't affect the probability of A. Since 0.45 and 0.5, which is 1/2, are different from each other, probability of A and the probability of A given B are different, that means they're not independent. That given B changes that probability in some way. For number 4, we have a bowl containing 3 red marbles and 2 black marbles. Delightful. And 2 marbles are selected at random in class. Many students asked about this. They're not replaced. Their colors are recorded. The probability of the first one being red and the second one being red is the following probability. Notice that this denominator went down by 1 because we didn't put the marble back. 3/10 is our answer. If probability that neither marble is red is the one that we're looking for, if they're both not red, they gotta be black, which means the first one is black, the second one is black. Here's your probabilities. Well, the probability that both marbles are different colors, there's this way that you can do it, but there's another way. You can figure out the probability of the first one being red and then the second black. If you figure out that probability, you're multiplying 2 fractions together. You're going to multiply 3 out of 5 times 2, because there's 2 black marbles, out of 4, because there's 4 remaining total marbles. That should be equal to 6/20. But that's not enough because you need to figure out the probability of the other outcome, the probability of the first one being black and the second one being red. Easily figured out by multiplying the first black, which was 2 out of 5, times the second red, which is going to be 3, because there's 3 red marbles still, out of 4. So 2 out of 5 times 3 out of 4, that's going to give you 6 out of 20. So that in total, when you add those together, that's going to give you 12 out of 20. For number 5, a single die is tossed. The number of dots on the upper face is observed. We wrote out the sample space here, or I wrote the sample space, because you guys didn't do anything. I wrote out the sample space of number greater than 2, and the sample space of even number. These are our desired outcomes. Here's the entire sample space of everything that was possible, and we use this to calculate the probability of A. Well, there's 4 desired outcomes, 6 possible, so 4 out of 6. We simplify that for convenience sake. The probability of B is 3 over 6, which means there's 3 desired outcomes over 6 total, which is equal to 1/2. A and B, listen, all we did was we went through and figured out all of the ones that count for A and the ones that count for B. In other words, we looked for the overlaps, the ones that are in both. We got a 4 that's in both. We also have a 6 that's in both. So we get 2 possible outcomes over 6. 2 desired outcomes over 6 possible. That's 1/3. We used our formula for the probability of A or B. It's A plus B minus A and B. We knew A and B from the previous problem here, so we were able to figure it out fairly effectively. The probability of A given B, we used the formula from before, A and B over B. That's 1/3 over 1/2, and you can easily figure out any fraction like this, 1/3 divided by 1/2, by putting in the calculator. What we did here, or what I did, you guys didn't do anything, as I said, was I made the denominators equal to each other. Once they're equal to each other, we can eliminate them. 2 over 6, 3 over 6, that's just the same as 2/3. And the same thing with the probability of B given A. However, the A is the one that's on the denominator because given always has to be in the denominator. Anyway, that's 1/3 divided by 2/3, 1/2. Easy stuff. Sorry this is so blurry, my camera phone is bad. A survey of a group of adults visiting an urgent care center classified a large group of adults. You can read this. We did some totals, we did some column totals and row totals, and it should make sense to you that these totals add up to 1, and these totals add up to 1 because 0.4 plus 0.6 is equal to 1. That's all of the people. People either use glasses or don't use glasses. People either need glasses or don't need glasses. They're mutually exclusive, and they're also exhaustive. Exhaustive meaning you either need glasses or you don't. There's nothing in between. There's no third option. Anyway, the probability of people that need glasses, that's going to be, well, 0.38 plus 0.15. The probability of needing glasses but not using them, which is an unfortunate situation. You see a lot of blurry things in class. Need glasses, that's these guys, but don't use them, that's these guys. So there's your overlap. This is 0.15. Need glasses given he or she needs them. This is just an exercise in doing simple probability. Use and need, that's 0.38. That's why we put the 0.38 up there. Divided by all of the people that need. All the people that need, that's this column total here, that's 0.53. And then need and not use. Well, the probability of need and not use, that's need here, and not use, that's 0.15. That's why 0.15 is in the numerator there. And the not use people, he or she doesn't use them, that's going to be all these folks plus all these folks. That's going to be 0.6. 0.6 divided into 0.15 is 1/4, or 0.25. Anywho, in this case, 60% of people surveyed at an amusement park can swim. I put uh-oh because the alternative is not swimming, otherwise known as sinking. Explain why x is a binomial random variable. Well, there are a couple of things we need to know about binomial random variables. One thing that you must know about a binomial random variable is that they have a success or a failure. Success is going to be p, and failure is going to be 1 minus p. Well, we have our probability of success, and it is not going to change. That probability doesn't change based on the first person sinking or the second person sinking or whatever. 60% of people surveyed at an amusement park can swim. That means that that's not going to change. The trials are independent, which means one swimmer doesn't affect another. That's what I was kind of saying before. We also know that with binomial random variables, the number has to be static. We can't have this number changing. The number of trials has to be set in stone. It's not like we're going to ask people until we find 5 people that swim. It says we're only going to select 5 people. So that number being static is super important. All right, so hopefully I've convinced you that this is a binomial random variable. They have a set probability of success. They have a set number of trials, and they should also have trials that are independent in nature. It also asks for success and failure. That's well, we know success means you can swim, failure means you sink. The probability of success is 0.6, and failure should make sense at 0.4. Here we did what's called a binomial, the binomial formula for 4 successes. N is 5, which means we asked 5 people. 4 is the number of people we want to swim. That 4 is the exponent under successes because we want 4 successes. We want 1 failure, 1 dude or dudette that does not know how to swim. So we multiply that all together and we get 0.2592. Have fun. At least 4 cannot swim. So that means 4 non-swimmers or 5 non-swimmers. If we're putting it in the terms of a problem, though, we want 1 swimmer. In other words, 4 non-swimmers. We want 1 success, or we want no successes. So this first one is the probability of 1 success. I'm sorry, this probability is the probability of 0 successes, which means 5 failures. Over here, this is the probability of 1 success. 1 success, 4 failures. See how that works? And these exponents always have to add up to, you guessed it, they always have to add up to 5. That's the n, that's the number of trials. We ask if this is a valid probability distribution. Well, we know that this probability is positive, and between 0 and 1. So is this, so is this, so is this. And then over here we said the sum of the probabilities is equal to 1, which means 0.2 plus 0.4 plus 0.3 plus 0.1. That's equal to 1. In order to find the expected value, we multiply probability. You should remember this, the probability times the payout. The probability times the payout. Probability times payout. Probability times payout. That's how you find the expected value of a probability distribution. A random experiment consists of tossing 3 coins and recording the number of coins which land heads up. This is a fun little tree diagram that helps you figure out that structure. Another way that you can do it is multiply it out. Another way you can do it is use the same binomial formula that we used before here. But in generally speaking, when I get 0 heads on my coins, the probability of that is 1/8. Then 1 head is 3/8, 2 heads is 3/8, and 3 heads is 1/8. You can tell that this is a probability distribution by, well, simply adding these probabilities together. Guess what you get? That's right, you get 1. You can also tell because all of these probabilities are between 0 and 1, which means it is a valid probability distribution. We know that when you're flipping 3 coins, you can have either 3 heads, or 2 heads and 1 tail, or 1 head and 2 tails, or 0 heads, 3 tails if you're extremely unlucky. Moving on to question number 10. We did the same thing here that we did for the previous problem, except we already had the row totals and the column totals, or at least some of them. We just back solved to find them. For example, 45 subtracted by 18 and subtracted by 16 is going to give you 11, which means 18, 16, and 11 add up to 45. I urge you to take a look at these and try to figure out why I did them. Should be fairly straightforward. In order to find these probabilities, it's very similar to the previous problem that we did. You can figure out these probabilities by using the formula, or is the first one plus the second one minus the overlap. And also, and is going to be calculated by simply looking at the table. For the extra credit, as I wrote here, you're on your own for this one. Good luck. Keep in mind that I'm not going to ask you to do this type of problem for the test. All right, thank you for watching this video. This was, again, a review of the test number 2. I hope you have good luck studying.